What's up, everybody? This is Matt Brown with another IoT hacking video. Today we have a new device to take a look at. It is the Wyze Smart Scale, and we have it apart over on our workbench. What's cool about this device, if you followed my channel for a while, usually most of the time I'm looking at Linux-based devices and everything that entails. Dumping flash is pretty easy because that flash chip is external to the main CPU. Well, today we are targeting a microcontroller based device, and so we are going to have to dump some internal flash. Can we do it? We will find out. So let's go over to the desk and see what we're dealing with. If you're new here, please hit subscribe if you like hardware hacking related content, and that's all I'll say about that. Let's go to the workbench. So over here, if we zoom out a little bit, so yeah, you can see I've got the guts of my scale open on the back side here, and this back cover popped off pretty easily. The device is powered by these 4 AAA batteries, and I'm actually going to take one of those out so we power off the device for now. And yeah, so if you're not familiar with these scales, obviously they will take your weight, but there's also some additional functionality in here. There are these electrodes, and what they do on these smart scales is they actually run current through your body, and there's some magical science that happens. And if you have a different distribution of body fat and muscle, you have a different resistance level, and you can do some math and determine, roughly how much body fat you have. So we are going to take a look at this device even closer. So I'm going to bring my microscope over here, and what we're not going to look at. So there's kind of like 2 big chips here. There's this guy right here, and we can kind of zoom in on that, and if we look sideways a little bit, have the light angled the right way, we can see printed on there, it says Chipsea. So chip and then sea, like the body of water. So that's pretty fascinating because that is not a company that I have heard of before I took a look at this device. So we are going to dig into that more later. But this chip we're not going to look at today, but this is actually really fascinating piece of technology here. It is a very special built chip that does the function that I just described on a smart scale. It takes in the electrical measurements from running a current through your body and then outputs over its UART line, and you can kind of see these traces, which is really cool. We're going to look at these a little bit later, and I assume that data, and by later I mean in a different video, I assume we have these like UART lines where it runs that data. That kind of looks like it's going over here. Anyway, we clearly see some traces going between this chip and then this chip, which is what we're going to be targeting today. And so obviously what's going to happen is it's going to take those sensor readings and then it's going to calculate, how much body fat it thinks the person has, and then it's going to communicate that over. And this is the Bluetooth chip that is going to do all the heavy lifting for us. And so we're going to actually be targeting in this video this microcontroller, and then we might do some fun analysis of the data passing between those 2 chips in a future video. So really fascinating product. But here you can see that right next door I have what is clearly a nice set of test pads for my microcontroller. Now we're going to zoom in on this and get this in focus and then try to be able to read what's on that chip. This is very tiny, and it did take a while to be able to successfully read that. And if I shine a light sideways on it, sometimes that actually helps. Aha, there you go. And you can see right there that we have another chip from Chipsea. And so this is the Chipsea 92F25, and then some other numbers. So we are going to take a look at this chip's datasheet because it is a fascinating journey of reverse engineering fun. And when I say fun, I mean staring at a data sheet that is mostly written in Chinese, which I do not speak. But I do speak Google Translate. And so we can, come to this data sheet and, go to the section that we think is obviously like the general description, like big picture, what does this chip do? Yeah, and all the specs, okay? Obviously, you can see some of the English, acronyms and stuff like that coming through, but we can just chuck this into Google Translate and we can understand some data sheets. So this chip, the Chipsea 92F25 is a highly integrated blah blah blah. It's a Bluetooth chip, so it does Bluetooth low energy, Bluetooth 5.0. And it has and this is very important for our next piece here, it has a Cortex M0 core, and then it's got some flash, and it's got some SRAM. Those are going to be important for later too. And blah, 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 low power, of course, is Bluetooth, battery-powered Bluetooth device. Here we go, a bunch of specs, kind of just regurgitating what we just talked about. So that's awesome. And what we don't see here, which is quite interesting, is anything about the security features. So let's go and say, okay, maybe it's in one of these sections. Maybe it's in the table of contents. Gosh, copying and pasting PDFs is the worst, right? All right, so just gonna copy this blob of stuff into here, and okay, blah blah blah, Chipsea, it's Shenzhen, China. No surprises there, and we can kind of see. Okay, these are the different sections in the table of contents. Product overview, pin configuration. That is really interesting, and it turns out to not matter for our case, but. There are some interesting pins, boot pins that you can pull high or low and set the device into like a bootloader mode or so, like various different modes. Turns out we don't even need to mess with that stuff. So CPU, memory, power, interrupts, a whole bunch of stuff here. Okay, yeah, GPIO, UART, that's all great. That's all awesome. So, so far, I don't see anything in there about like security, about any kind of a firmware readout protection. And so, obviously that could be somewhere later in the document. So what we're going to do next is we're going to find, so here we have the pinout of the device, which is super helpful. And we're going to go down here and see the detailed listings of all the pins, right? Because this is an ARM-based device, so the debugging interface is going to be serial wire debug, SWD. And so we are going to be looking for those, and we're actually staring at them right here. So again, oftentimes, even in these Chinese data sheets, the acronyms will still be in plain English. And so here, staring us right in the face is SWD IO and SWD clock. So that's basically what you need. You need those two wires, you need ground, and then we'll talk about how we're gonna need a couple other things to get our debugger to interface with serial wire debug. But here we can see that pin 5 on the chip is that serial wire debug, and then and it says it's also known as P02, and then the clock is also known as P03, which again will be very helpful to us. So let's just go and let's just look for those two pins, and then I'll show you some of the other pins that I'm going to need to when I'm on the board. But I want to show where these are located. Okay, so here's pin 1, and then down the side is where we're going to find these pins 5 and 6 right there. So let's go back over under the microscope and kind of just trace these so we can get a little more light. And so again, we have a pin 1 indicator, kind of hard to see here, but a little easier to see here. So 1, 2, 3, 4, 5, and 6. So these two pins right here are for the IO and the clock pin. And we can, if we can see in the right light, we can see those traces going directly over here. Oh wait, what's that? P02 and P03, just like they're documented in the data sheet. like I was mentioning, it would be really interesting to see what the bootloader mode for this device is, because as you can see, there's these 3 boot pins that you can kind of like pull them high or low, and they do stuff. But here we have found our debug pins to get serial wire debug working. We have a nice ground pin to work with. That's all awesome. And I'm going to show you 2 more pins that I'm going to connect to, because when I start connecting up these little pogo pins, they're going to kind of all be stacked on each other, and it might be hard to see. So the one other thing I'm going to need, there's 2 other things, is this reset pin, and that's going to allow my debugger to reset, like send the reset signal to the chip, which sometimes works, and sometimes we just have to manually reset the device. We'll talk about that later. And then we have VDD, which is just a voltage reference. And so our JLink debugger, which we will be using to perform our debugging of this chip, is going to need a reference voltage. And so we are going to, actually, what we can do right now is we can flip on this. We can go to voltage mode, and we can probe this. Let me find, switch hands, ground right here. I do have to plug in the device, that helps. All right. And then we will see that we are operating at roughly 3.3 volts for the voltage reference. And so when we set up our debugger, that is what we should see for the reference voltage. And we'll talk about that once we load our debugger software. So now we can switch over to this camera view, and we are going to hook up our JLink debugger, and I have 1, 2, 3, 4, 5 wires connected out of this, and then I have a whole mess of PC byte probes that we're going to attach to our device. Okay, before we do that, I'm gonna flip over here, and I'm just gonna give you kind of a like, that's not what I want. No, view the file. Okay, so this is just a kind of a view at what the pinout on the JLink connector is, and we're going to kind of talk about on this diagram what I'm using, because it'll be hard to see when I'm setting it up over there. So first we have the voltage target reference, and so that is what we're going to be connecting to that voltage line that we just measured as 3.3 volts, and so that's going to let the JLink know again what the target voltage on the device is. And then we have the target reset pin here that we are going to connect to the reset pad that we found on the board. And then down here we have the target, oh gosh, see, I always forget for SWD. Okay, yeah, we do these ones. We do 7 and 9. These are labeled, I believe, for JTAG and not for SWD. But just trust me, bro, that we're going to be using pins. So we skip this pin, and we're gonna use this one and this pin. So this is the data pin, the IO pin, and this is the clock. And then we just have a ground connected to any of the ground pins over here. So those are our 5 pins. Let's go back over here, and you can watch me try to hook up all of these pogo pins. I'm just gonna take one of these batteries out again so we make sure our target goes down. Okay, so this is going to connect to ground. Here, you can have a really high-res picture of my pain as I set these all up. Okay, next, okay, those go like that. And now, okay, gosh. All right, I'm gonna find the voltage reference because I want to get this one kind of down here. Okay, there's voltage reference, and here is ground. And then I have my 2, these ones are lined up already, I do know that. So to P02. And then, like I said, you're not going to be able to really see this, and this is going to go to the reset It's kind of hiding underneath one of the other ones. All right, so we're just going to check. We're on the pads. There we go. Ground and voltage reference. There we go. I think those are all connected. And now I'm going to very carefully try not to bump this and plug in my debugger. And let's come over to my computer and we're going to talk about what we're going to do here. So I've got this JLink script here. And actually here, we'll do it manually and then I'll show you the script that I'm going to use to interact with the device. So we're going to go JLink exe and we're going to get a, oh yeah, so the voltage reference is 0. It's measuring 0 volts and that's correct because I took this out. Gosh, I bumped that way too much. Okay, hey, we got 3.3 volts. That's good. Now we're going to say connect. Now, the device is this kind of generic Cortex M0, right? The JLink does not have a chip profile for, you know, Chipsea, this super random and obscure microcontroller out there, right? So we're just going to have this generic Cortex M target, which should be fine. So I've already selected that, but I can hit that again, and then I'm going to hit S for SWD, because again, this is an ARM target. I have it wired up for SWD, and then we're just going to hit yes for the default speed, and yes, this is educational content, guys. All right, and then it's going to tell me, oh, it failed, right? Well, the thing about this scale, right, is it's designed to really sip power, not use up the batteries really fast. And so what I've noticed is that the debugger, you can really only interact with it like right away on boot. So I am going to take the battery out, put the battery back in, hit connect, enter S, enter. And here we can see that, you know, can I read like some memory out? Yay, we can read. Okay, so now I can debug, and if I wait like 15 seconds, yeah, I won't be able to do it anymore. But we have this script, which is going to perform a bunch of these actions for us. And so here we are going to, some of it is going to be like passes command line flags, but in the script, it's going to set the speed to 4,000, and then we're going to run these 2 commands, which are important. Oh yes, and we need to go back to the datasheet to see why the heck am I dumping the flash and the SRAM from these 2 locations. Well, let's go back and let's look at that datasheet, because if I scroll down somewhere here, we have this nice little map of the system memory. And so we can see right here, we have the 512K of flash, and we can, if we zoom in, because that's really small. All right, we can see, let's go back a little bit. There we go. We can see right here that, you know, 11000000 is the start address for the flash, and then you calculate the offset, right, or for how large it is. And then the same thing with SRAM, and they have it labeled as like SRAM 0, 1, and 2, and I'm just going to dump the whole thing. So I'm going to dump all the way from here up to this address, and so you do some math, and then you end up with these things right here. Oh yeah, I got to do this so we don't have any problems. All right, so that's our script, pretty simple. And what we're going to do is we're going to try to remember JLink. Yeah, we're going to run it like this. Clear. Okay, so right here we're running, yeah, the JLink exe file, and we're passing it on the command line, that device, so we don't have to like go through the interactive menu. And we're going to set up the interface to be SWD, and then it runs those commands inside the script, and so it should run pretty quick. Again, we're going to take the battery out, and we're going to drop it on the ground, and we're going to pick it back up, and we're going to run our script. And it read our 2 files. Nice. So here we go. We've got flash and SRAM and the sizes that we expected, which is pretty awesome. So we can just to kind of do a sanity check to be like, hey, is there any real data in here? Yeah, we can run strings on the flash, and we get a printout about the Chipsea something something. We get you know, some random, you know, pieces of data there. Let's like rep for BLE. Okay, maybe like, okay, so there's something that has to do with Bluetooth on here, right? This is a scale, so like your weight. Oh, okay, there's some stuff about the types of data that are specifically on this scale, which is pretty cool. Then we can do the same thing for the SRAM, just again, okay, cool. There's some cool strings. There's some strings that are not really strings. But yeah, so now it seems like we have successfully dumped from this device the flash and the SRAM, which is pretty cool, right? There was no like protection, there's no readout protections. And again, based on this data sheet, I fed it into, you know, I fed it to Grok, and I fed it, you know, a bunch of sections to Google Translate, and I can't seem to find that it has any kind of readout protections like your mainstream microcontrollers would have. So if it does, it's not being implemented, and you can just pull all the data off the chip, which is pretty cool. So what we're going to do now is just for fun, we're just going to kind of get started a little bit with some reverse engineering. So we're going to talk about what it would look like to load this binary up into IDA Pro. And so we're opening IDA Pro here, and we're going to open this binary. I know based on the target that this is ARM little endian is the architecture. And so we're just going to go ahead and hit OK. And then here is a very important part, because here this is ROM. So this flash section is going to contain code, right? And so what we're going to have to do is we're going to have to set the start address, which is this guy right here. And it already knows what the size is. That's great. And we don't need any offsets from the input file. So we're going to load this as a ROM section. Oh yeah, I forgot you have to like tell it that is at that address. There we go. And do you want to disassemble as 64-bit code? No, we don't want to do that. And we're just going to hit OK through all that stuff, and we're going to let it do its thing. And it pretty quickly analyzes. This is a really small binary. It analyzes it pretty quick. And so we are going to start to, we can, oh yeah, so, oh, no. Before we do any analysis, we want to load the SRAM section. So we want to load the other binary and have it be at its correct address. So we're going to go load file, additional binary file, and we're going to select that SRAM bin. And so here, this is really important, and this actually took me a little while to figure out what the heck I was supposed to do here. So this, you actually want it to be 0. Loading offset is actually the address where where it exists in the flash chip. Again, so that's that start address for the SRAM. And then we leave all this stuff. And then I need to uncheck that this is not a code segment, right? This is a data segment. As far as I know, there's no executable code in it. So we're going to uncheck that. And we're going to hit OK. And now it's loaded that in. So if we go to our hex view, so obviously we've got, you know, right here, we've got the code, you know, we've got the flash in its proper address range. If we scroll way down, we see 1FFF. Now we have all that SRAM in its proper address space. So the cool thing now that we have both of those set up is we can start to do some reversing. So I'm going to go to View, Open Subview, and Strings. I'm a little new to IDA Pro, guys, but you know, just yeah. All right, now let's look for some cool strings. You know, like, okay, oh, here we go. Okay, so this device, so this is pretty cool, right? So this device, there's no firmware readout protections. It has information about your weight, your height. So it's not reading your height, right, from the scale. That's clearly something that you as a user are inputting via the app, and then it's sending it over BLE. So your height, sex, age, athletic type, the scale I looked at before, it was like yes and no. Like, are you athletic? Yes or no? But yeah, so this data is clearly being loaded into the scale, which now doesn't have any firmware, like any flash readout protections, which is kind of interesting. So if we go to this string, we can, see, this is where I'm like a noob at this, guys. All right, here we go. If we go and look at this main view right here, we can see it was kind of given like a name here, a weight, d height, this thing. And so we can say list cross references to, so tell us like any functions where that string gets used, and there's one place right here. And so we can we see right here that it is being used, and I can hit F5 to decompile that, which is pretty cool. So here we can see that there's clearly like this function. So this function is obviously some kind of like print function, right? It's taking in strings with format strings, so it's probably printf, right? And then it's taking a buffer. So this is pretty cool because it is, you know, it's clearly having all this kind of data located on the scale, which you can read out. So right here, if we go to this, oh yeah, this is super cool too. So see how these functions are taking in data from SRAM. Look at that, 1FFF. So if I go here, I can jump over here. Now I have not loaded, I haven't even set this scale up yet. I've set some of my other scales up, but what I want to do now is set them up, and what I would assume to see are in these kind of structures here stored in SRAM will be user data, right? Like you'll have the codes for your weight, height, sex, all that information will be located here in SRAM, which would be pretty fun. So that is just a little bit of a preview on the start of this project. I actually started looking at this scale for a completely different purpose. I wanted to do some fault injection, and I wanted to find a target that had a microcontroller that was locked. And so I was like, okay, I need to make sure that it's locked with my JLink debugger, and it turns out it was unlocked, and so here we are. So next video, hopefully we can, well, in some other videos, hopefully I can find a locked microcontroller target and we can do some glitching. And then also with this one, I'm super interested to see what the data looks like on, you know, probably UART or whatever the interface is, where that super specialized chip that does the body composition calculations and how it sends it to our other microcontroller, and just talking about, you know, physical data security in that context. So thank you for watching this video. Please like, comment, and subscribe, and definitely join our Discord. That link's down in the description as well. Have a good day.